Hey YouTube, it's Dimitri, and today we're going to do time series video continued. This is video 16, I believe, and we're going to just do a simple model. I was planning on just doing a simple model, looking at a few things, and then just like scrapping it and moving on to other methods. But as I dig in deeper and I spend more time kind of working with the code, I want to show you guys more of the hands-on looking at models, building models, and then saying, hey, this is okay, but how do I dig deeper? What do I look for? What's wrong with it? How do I make it better? So we might wrestle with this for a little bit. I'm not sure how long I'm going to go down the rabbit hole of the simple analytical approach, but we're going to do it. We're going to do some testing. We're going to throw it all together. But I want to show you guys, you can explore all kinds of stuff above and beyond what we're going to do in the video. And in practice, if you're a model developer, you should be going the extra mile, the extra 10 miles, the extra 100 miles to really nail down how your model works, understand where it fails, and sometimes understanding that failure is okay, but being able to like explicitly list it out and say, hey, this is a weakness in my model, so that the model user, whoever's using it, knows like, okay, it does fairly well, however, there's this issue. So anyways, let's dive into this real quick and just get going with the code. We're going to run all the code from last week and the week before and all that. If you have this project saved, you don't need to rerun everything because everything in the top right corner should already be saved. Okay, so everything from the last week, we're just going to rerun it. If you already have this ran, if you already saved the project, there's no reason to rerun it. You'll have all your data up here in the right-hand corner, but let me just run this real quick. And before I do that, I'm going to comment out the stationarity testing that we already looked at, just because it takes a long time to run. All right, and we'll close some of these data windows. Okay, so if you start from video 15, you're at the end of it, and you're all ready to run, you should see this chart in the bottom right with the red and blue lines, and the gray bars showing where we took the snapshots. Okay, and we're just going to build onto this file here. So as I said before, tmin is going to be our variable that we're going to model. And in statistics, we call this the dependent variable. Independent variables will be the variables that are going into the right-hand side of the equation to model it. But let's start off with what I like to call a common sense model here. And so common sense would tell me from looking at this blue and red chart, which we're just going to be modeling the blue, there is an annual component. So it looks like every peak is going to be 1 year apart. Every trough is 1 year apart. Every middle part of the line will be 1 year apart. So it's kind of, I guess, practical to say that let's just use an average based on the month day. So what I mean by this is January 1st this year, if we're going to predict it, should be some sort of average or past value from other January 1st, right? We should see a similar trend and a similar pattern. We're just going to assume that to start with. Again, it's going to be an okay model, a simple assumption, but let's see how it performs as we get going. I want to put in here, you need to have expertise on what you're doing. So as different problems occur, if you're working in the health industry, for example, you should have health background information, or you need to interview people that work there that you're building the model for extensively to be able to do this. In finance, again, having a finance background is helpful. It does not make the world and make you this amazing developer. Again, knowing all this stats, modeling, hands-on math is extremely important. But again, you need to know the problems. You need to know the finance. A lot of times portfolios are different from bank to bank. So even if you understand basic finance, you do need to go talk to your developers and say, hey, let's say we have, a mortgage portfolio. Is it mainly commercial? Is it retail? What is this, the duration of these? Are these typically like 5-year mortgages, 20 years, 10 years, 30 years? All that's helpful. So one thing to note about calendars, so things that we should know, is that there's going to be a leap year, which is going to mean that there should be a February 29th and then your year here in your data. So we want to make sure we capture this. What we're looking for is, we should see 366 daily values. And we could dive into all the details on leap years, but I'm not going to go into that. just keep that in mind. We need that in the data. If not, if you end up building a model without it, then it has no way to predict it. So we could do a little workaround there, like a computer science workaround, and say, hey, if 229, then pull 228. That's a solution, but it's okay. We have it in our data. So in general, we're going to call this an analytics model approach. Again, I use the word model here very loosely. I consider it a non-model, but this is how you would do it with simple analytics. Okay, so to start off with here, we need to group the data by month and day. Since we have a yearly trend, right, we don't need to keep the year in there. The easiest way to do this is take dev, which is going to be our development data set, and we're going to create a variable called month day. And then we're just going to use the substring function. And then we're just going to take the substring of dev date. And if you look at it, so I don't have it up here, but let's open one real quick, just so you can see. The date is going to be year, month, day. So we're going to want to take the 6th, 7th, 8th, 9th, and 10th value from this string, because we want to drop the beginning part, which is the year and the dash. So in our code here, we're going to say, okay, we're going to substring the date. We're going to start at 6, and we're going to go to 10 on the placement. And we're going to hit run. Again, if you want to view that, you can go back up here to dev and look. So it looks like it's correct, right? Month day is going to be the month, which is January 1st, which are here. And then the month day for the second one is going to be January 2nd, January 3rd. So it looks like it works. And again, if you want to scroll on to the bottom, you can see 12/31 of 2014 is the last day in our data set. Again, there's no years, and that's good. That's what we want. Okay, and next we're going to want to take the mean of the month day variables and basically do it for all the data we have from 2010 to 2014. That's 5 years. So we want to take the mean. So let's just put take the mean by month day as the variable. And to do that, we're going to do prediction, or pred is what we're going to call it. And we're going to type in aggregate. And we're going to say, okay, x is going to be equal to what we're going to be modeling here. So dev team in. And we want to group these by, use the list function here. And we're going to do dev month day. And then we're going to end that parentheses, put a comma, and then put fun, which is going to stand for function, is equal to mean. Okay. I believe you can type out fun if you want and just type in function. We're just going to put fun in here though. Okay, and we're going to hit run. So let's run this real quick. And as you'll see, it creates something called prediction. I don't like that it has the group 1 here. I like to keep the names consistent. So we're going to go back here and we're going to rename this. So I'll type in call names here because we want to do the column name. We want to do it for the prediction data set that we're using. And then do square brackets and do 1, so it's the first column. And then we're going to set this equal to Monday. And we're going to run that. If you go back here and look at prediction, now our first column is called month day. X is going to be our predicted value. So if you want to check this out real quick, you can look at, okay, January 1st is going to be 34 degrees. You also notice there's 366 observations, which is exactly what we were talking about earlier. So there is a leap year in there. And if you scroll through the data, you can visually see there's 366 observations, and December 31st on average is 35.4 degrees here in Dallas. Okay, so now that we have this is basically like a prediction scoring set or an equation, right? It's not really a math equation, but it just has each date has some value. The value that we took, we aggregated here by the mean given the month day of our data here. So it should be 5 past values that calculate this. All right, so now we want to score our data itself. So if you look here, we have prediction, which is 366 observations. I want to apply that now back to the development data set so we can score all of them. All January 1st should have the exact same value. So we're going to apply the data by date. which is more specifically, we're going to use the month day to do this. We're going to call this dev2. I'm creating a new data set just because I want to maintain my development one a little bit cleaner, and I don't know, I save it for other purposes. You could overwrite it here and just add these in. Again, if you're not quite excellent on writing code or you don't quite understand the function, writing a second data set is helpful, because if you screw it up and it doesn't apply it correctly, then you have a backup to redo, and you don't have to go back and rerun all your code. Anyways, so we're going to say dev2, and we're going to say merge. And we'd like to merge the development data set with the prediction data set, and we would like to merge it by the month day variable. So it's important now that the month day variable is in both data sets, which it is, and we're going to run that. And then we'll just type in view dev2. We'll run that real quick and look. So now if you look at the data set, we have January 1st, but it's over and over and over again. And it's 5 times, and it starts on January 2nd. But the key point here to look at is, okay, it has on the date column, right, 10, 11, 12, 13, 14. So it's sorted these by month day, not by the date, which is fine. But a quick quality control check will show you our minimum temperature for January 1st, 2010 was 27. We predicted 34. In 2011, it was 31. We predicted 34 again, right? But we want to sort this now by date, because that's how we logically think about this. And it's easier to chart and do things by date. And it's easier just to kind of look at it and make sure things are running correctly for other steps. So we're going to sort the data by date, by month, or by date. And to do that, you're just going to type in dev2, and we're going to take dev2, and we're going to do square bracket, type in order. So we're going to use the order function, and we're going to order this data by dev2 date. And we're going to run that. And remember to put in the comma here, because I forgot it. And we're going to run that. And then if you look at dev2, all of a sudden you see that the month day is January 1st, 2nd, 3rd, 4th, and the year's all the same. So we have it sorted back how we'd like to see it. Okay, so what we end up having here, though, like I just mentioned, is you essentially have the development data set, which was your date, your max, and your min temperatures. We're scoring the minimum one. We created some simple model, which was going to be the prediction model that we created with 366 different unique observations or predictions based on the month and day. And then we finally scored them, and now dev2 is a final scored data set. So we have it. At this point, let's just look at the errors. We'll measure out some of the errors, some error measures here. I'll talk about them briefly. And then we'll just score out of time 2, look at that real quick. And then I was going to try to hurry and dive into some issues with the errors as we look at them, and then we'll talk more about what's wrong with them. So we're going to type in here, we're going to put in measure the model's errors. And I'm going to use mean squared error just as something to kind of look at here. We're going to plot a ton of different metrics, and we'll talk a little bit about them. Okay, so before we measure the errors, we need to create the errors, right? So to do this, we're just going to create the errors quickly and say dev2 errors. So we're going to create a new variable inside of this dev2 data set. And all it's going to be is dev2 tmin, so our dependent variable minus our prediction here, which is going to be x. So we're going to type in dev2x. And then we'll run that. And you can go back up here to the tab and look at it real quick. So you see here, right, 27, 34, 27 minus 34 will give us -7. And so it looks like it's working as expected. And then finally here, we're going to use a variety of error measures. All of them have pros and cons, so you need to be wary of that. I do have a video which I might link below on different types of model errors. I believe it's part of the time series video series that we covered. But going in and out of the calculations, why some are better than others, can be an advantage or disadvantage depending on what type of model you're going to be using. But first, let's just do mean squared error. And to do this, we're just going to type in the mean of, and we're going to type in double brackets here because I'm going to type in dev2 of the error. Hold on. I'm going to rename the errors real quick to error, not errors, just because of the way I have my code written here. Okay, so we're going to take the mean squared error. So this is the error. We're going to use a caret, which is how you square things, and then put 2. So it's going to be the errors squared in the mean. So if you read this, it would be the mean squared errors. If you run this, this will give you our MSE, which we'll look at and talk about in a second. Next, we'll do the MAE, which is the mean absolute error. So again, this is going to be mean. Type in ABS, which is the absolute value. And we're just going to type in dev2 error. We're going to run that, and that's going to provide our mean squared error. And then finally, we're going to create our MAPE, which is our mean absolute percentage error. And this is going to be, so we'll start off with a parentheses, type in mean. And then we're going to type in ABS for the absolute value. And then we're going to type in our errors, so dev2 error, so $ error. And we're going to divide this by dev2 tmin. And then we're going to go outside of these 3 parentheses, and we're going to times it by 100. Okay, so this is going to seem a little confusing, but the error itself is going to be the actual minus the prediction divided by the actual. So that will give us our percentage error. So we convert that error into percentage error. And then with the absolute and the mean, we're going to end up with the mean absolute percentage error, which is going to be a percentage. You can leave it as a decimal. I don't really care. I usually look at them in decimal formats, but a lot of people like to see times 100, so it's in like percentage. So 5 means 5%, you know, things like that. So we're going to run that real quick. And so just quickly here, you see the MAE is 5.54, the MAPE is 11.88, and the MSE is going to be 52. So quickly here, the MAE is the mean absolute error. This means on average, we're off by 5.5 degrees. So if I predict, I don't know, 30 degrees, on average, I'm off by 5. So the real one's probably somewhere around 5.54. Since it is the absolute error though, I might be over 5, I might be under 5, but on average, we're just missing it by about 5 degrees. So if you're looking at this and you're building a model, let's say for farming, one aspect you could consider would be when should I plant my crop, right? I can't have it freezing, for example, or maybe it needs to be above a specific degree. So it needs to be above 42 degrees for us to plant some type of crop. You could use this model, but you might be off by 5 degrees. So a safety net for this would be, you know, looking at your data, going back, reviewing it. We're not going to do that right now, but figuring out how many cases are above 5 degrees. Maybe you should have a fudge space of 10 degrees. So you would use your model, predict it out, and then add whatever the fudge space you want. So I don't know, we're off by 5, usually 5.5, but 90% of my data falls within 10 degrees of error. So we would then say, okay, 42 plus 10, so when is it going to be 52 degrees? And then you'd pick that date based on the model on when you should start planting your crops. Again, this is important for businesses like farms because you need to plan ahead of time. You need to purchase seed, which is a lot of money and investment and timing and all that. It's not as simple as like you wait for the day to be the right temperature and then you magically gather a bunch of people and equipment and seed and everything and go out and plant it. So the MAE is pretty straightforward and simple to explain. The mean squared error is going to be a little challenging. It's 52.2556. It doesn't really have a lot of meaning for us right now because we're going to use this to compare to the other model. The MAPE is the mean absolute percentage error. So this is basically saying on average, we're off by about 11.88%. A keynote here though is that the MAPE can be used to compare across the same data but different models. So for example, dev to dev, but it's not usually useful if the data is too different. So if the data changes quite a bit between dev and out of time, and again, you can test for this, sometimes comparing the MAPE across the dev and the out of time might not give you the best results because the data might be significantly different. Again, MSE though we can use is a pretty standardized measure here. It's the mean squared error. We'll try to use this across different ones because it doesn't have a base. We're not dividing by anything. We don't have a percentage. But before we get too deep into the errors here, let's just go ahead and score the out of time data, and then we'll measure their errors real quick. So score out of time. And to do this, we are going to need to create the month day variable that we created for dev. So for scoring, and to do this, we're just going to say, okay, out of time, month day, and we're going to assign the substring again. We're going to do out of time, date, and then 6 and 10 as we used before. Okay, we can look at that real quick. That looks like it's working. January 1st, 2nd, 3rd, but again, we're starting in 2015 here. Okay, and then this is the important part here. So we are not going to retake averages or anything because we already built our so-called model, our analytics, on the development data set. We are now going to score the out-of-time data with the pred data from dev. So what this means is that we're going to take the prediction data set that we created on the development data, and we're going to use those values, and we're just going to score the out-of-time data. And to do that, all we're going to do is just do out-of-time 2. So we'll keep this consistent with development. And we create the predictions. We're going to add a 2 to it. And we're going to use the merge function again. Same code, just swapping out data set types. So we're going to take out-of-time. We're going to merge that with the prediction data set. And we're going to merge that by month day. All right, we'll run that. And then I'm just going to type out the errors here real quick. So out of time 2 error is going to be equal or assigned to out of time tmin minus out of time. All right, so out of time 2 min. So we're taking it from the second one. Minus out of time 2 x, as x was our prediction here. So we'll run that. And then we'll just type in view out of time 2 for good practice. And as you can see, we have the same problem as before. We have all the Januaries lumped together, but we do have our minimums, our predictions, and our errors already in here. So just to keep this clean here, so we're going to sort the data for human viewing. So again, we'll have out of time 2, and then we'll do square bracket, and we'll type in order, and we're going to order this by out of time 2 and by the date. Okay, we'll run that. And again, I always forget these commas in here. All right. Okay, and don't forget to assign it because when you don't assign it, it doesn't save it. Okay, so we'll run it, and then we'll open it up again. Okay, since we saved it this time, instead of just running it, you'll see now that we have it fixed and it's now plotted out by year. Okay, and now we're gonna look at our error metrics. And we're gonna do MSE, but we're gonna call it OOT. And this is gonna be the mean, just like above, of dev 2, or out of time 2, sorry, out of time 2. And then caret 2 to square that. And then we're gonna do our MAE underscore out of time, and that is going to be the same as above. So if you wanted, you could copy and paste for speed. I'm just going to type them out real quick. And we'll run that. And then finally, MAPE underscore out of time is going to be parentheses mean absolute out of time 2 error divided by out of time 2 tmin. And then we'll go outside all these parentheses, type in 100. All right, we've got them all. Okay, and now if you look here on the right, you can see we have them basically lined up alphabetically, which is perfect for what we're doing based on the way we named them. We have the MAEs you can compare. So the development one is 5.54, out of time is 6.23. Development beats out of time. MAPE, again, would be 11.88 versus 12.48. Development beats out of time. And mean squared error is going to be 52.2556, which beats 67.32. Again, it beats out of time. This is expected, guys. This is, we should know this. So it should be expected that your dev will beat your out of time. We will look at this later in detail here. But again, it beats it day in, day out. It doesn't matter if you're using stats, analytics, or time series modeling. It's always going to beat it. There are some rare occasions where your out of time might get better and it might improve. But in general, since we built the model on the development data, it should always fit that development data the best. And the entire reason for doing this, of adding the out of time here, or you'll see later in neural nets and stats models, similar concepts, the reason that we do this is we want to see how well it performs. So again, the MAE is the easiest to understand for this aspect in modeling here. We're off by 5.5 degrees on average. With the out of time, we're off by 6.23. It's 1 degree, give or take, a little bit less than 1 degree. It's not too bad, okay? But we're gonna build other models. We're gonna look at other models. Then you can come back from a bigger, high standpoint and look at it and say, okay, the super simple analytical tool that we built performs based on these metrics, this amount. We had this awesome stats model, which is slightly complicated, which performs this amount. We have maybe a super complicated stats models, which has this performance. And then finally, we have like a neural network or one or two of those we've tuned and looked at, and they perform in the following way. So you can compare them across and see which models work the best for you and the best for your applications. And again, I highly, highly encourage you guys here, do not pick the model always based on whichever one has the best metrics. A lot of times a very simple and intuitive model is far easier for the end user. So I don't know, if you're a trader or you're a farmer or I don't know, whoever's using this, it might be super easy and quick in stressful situations to say, hey, we're off by on average, 5 degrees, 6 degrees, whatever, and then make a decision quickly, versus if you have some model and there's a bunch of other stuff baked in and a bunch of other factors coming into it, and temperature and humidity and like all this other complicated stuff, then they might have to think things through a little more, and it might be better to take the simple model. So simple doesn't always beat complex, but complex definitely does not always beat simple. Weighing your options and looking at the model usage is a very important aspect of model development. Anyways, I'm just going to copy and paste in my error notes here some things just so you can see them. They don't really mean anything too much, but it's just what's summarizing what I just said. Anyways, thanks for watching this video. We still have a long ways to go just looking at the errors here. I'm going to create a second video now. We're going to quickly go through some deeper analytics and kind of listen to our errors in the model and see what's going on. But anyways, thanks for watching. Don't forget to like, share, and subscribe. And as always, until next time.